All right, welcome to worksheet number 2, limit laws. Here we'll talk about calculating different limits using the limit laws. This corresponds to section 1.6 in our textbook. So in the previous section, we talked about limit, definition of limit. We plug in a bunch of different numbers to kind of estimate the limit. But do we always have to go through the long process to calculate the limit? In this section, we'll discuss an easier way to calculate the limit. So let's look at some properties. We have two functions f and g. Limit of f of x as x goes to a is equal to L. And then limit for g of x as x goes to a is equal to m. And c is just a constant number. It's just a fixed number. So we have a bunch of different limit laws here. If you take the limit of a constant, there's no x in it, so that number will be just the limit. I can add two functions. I can multiply functions, I can divide the functions, and basically the limit will be just the sum of the limits, right? And then you can take the exponent. So we'll be kind of using these properties to calculate the limit like in an easier way. For number 6, one thing I want you to kind of notice that it's a function f over g, so a function over the function. It's called rational function. I want to make sure that the denominator, the bottom, is not equal to 0. So again, when we have a fraction, we do not want to have a 0 denominator. When you have 0 denominator as a limit, that's when you have to do some extra work to figure out what the actual limit is. Okay, let's look at example number 1. We have function f of x. The limit of that is 2 as x approaches to a, and g of x limit is 3. And then h limit is 0. Let's look at number 1, limit of f plus g. So I'm adding two functions. So what's the limit of the new function where you added two functions? Basically, what the limit law says is you can just add individual limits. So f of x has limit 2, g of x is limit 3. So basically, that's that. So it seems like I'm not really doing anything. It kind of works nicely like that. Number 2, I noticed that two functions are multiplied. Kind of same thing. You get new function by multiplying two functions. So how do you find the limit? Basically, I can look at the limit of each function separately and multiply the answer. So it'll be 2 times 3, which is 6. And for number 3, square root of the function f of x. So the answer will be square root of the limit, which is 2, right? So, and then number 4, h over f. The limit of h is equal to 0. Limit of f is equal to 2. Oh, there's a 0 in the fraction. Is it okay to have 0 in the fraction? It's okay to have it on the top. 0 over 2 will be just equal to 0, so no problem there. Number 5, this might be a little bit tricky one. I have f on the top. I have h on the bottom. So according to our limit law, it's going to be 2 over 0. Again, I mentioned before, 0 denominator. So here does not exist. 2 over 0 is either positive infinity or negative infinity. That means it's not a fixed number, so the limit doesn't exist. So I'll write DNE for does not exist. Let's look at example 2. Kind of similar situation. I have three functions. Limit of x squared function, 3x function, and then plus 1 function. So this function minus this function plus this function. So how do you calculate the limit? Well, first, the function is x squared. So when x approaches 2, x is going to 2. And there's a square function, so the limit of that is going to be 2 squared, which is going to be, so 2 squared. Same thing is 3 times x. So when x approaches 2, x will go to 2. 3 times that is going to be 6. And then plus 1. So that'll be 4 minus 6 plus 1. So that'll be negative 1. So it seems like we're not really doing much here, which is kind of case for the polynomial. So let's look at the next theorem here. If p of x is polynomial function, then the limit of p of x as x approaches to a is basically p of a. That just means plug in a into the function. Right? Polynomial is basically a nice function. So polynomial. For example, it looks like 3x fourth plus 5x squared minus 3x plus 5, whatever. So it's all just number times x to the some power. So generally speaking, it'd be like a n x to the n power, a n minus 1 x to the n minus 1 power, all the way to a1 x to the 1 power plus a naught, which is just a number. So it looks like this: number x to the n power, number x to the some other power, number x to the 1 power, and a number. So the previous example we looked at, like here, this is an example of a polynomial, x squared, and then number times x, and then the number itself, right? So basically what it says is, if you have a polynomial and you have to calculate the limit, basically you can just plug in that number into the function, right? So extra example, if I have p of x is, let's use that, p of x is 3x4, 5x squared minus 3x plus 5. So if that's the case, the limit of x goes to 1, p of x, the one that I just gave you right here, will be, how do you find the limit? Basically, you just have to plug it in. So 3 times 1 to the 4th, which is 1, 5 times x squared, which is 1, minus 3 times 1 plus 5, right? And that will be 10. So finding the limit of a polynomial is pretty easy. You just have to plug it in. That's it. Next corollary has, if you have a polynomial of a polynomial, then you can kind of do the same thing. So even if you have a fraction, how do you find the limit? You just plug it in, then you get the answer. Again, here, provided that the bottom part, the denominator, is not equal to 0. All right, I'm going to have you guys pause and have you try part A and part B of example 3. And once you're done, let's meet at part C. All right, so you should have gotten -1/4 for part A and 2 for part B. Let's look at part C. Okay, part C says find the limit as x approaches to 3. I have x squared plus 2x minus 15 on the top, x minus 3 on the bottom. So my initial instinct was, can I just plug it in? So let's plug in x is equal to 3. Let's see what happens. On the top, I get 3 squared, 9, plus 2 times 3 is 6, minus 15, over 3 minus 3. That's 0 over 0. Okay, this is a case where I have 0 over 0. And we're going to kind of see this kind of cases again in the future. This is kind of interesting case. I know in fraction I cannot have 0 because I have something over 0 is it infinity or negative infinity. And I know in fraction, if you have 0 over anything, that's 0 as an answer. So this is an interesting case where you have 0 over 0. So generally speaking, when you have 0 over 0, let me make it red. If we have 0 over 0, that means we don't know what the answer is. We need more further investigation. We need further investigation. That means you have to do extra step to figure out what the limit is. As of now, I cannot say the limit doesn't exist. As of now, I cannot say the limit is equal to 0. I just have to do extra work to see if I can simplify something. So this is kind of a typical case where I have polynomial over polynomial. Maybe I can factor and simplify a little bit. So once I found out that this is 0 over 0 case, what I'll do is I can maybe factor. So here, x squared plus 2x minus 15. I can factor that x minus 3 and then x plus 5. So I can rewrite this over x minus 3 as x minus 3. And as you can notice, on the top is x minus 3 plus x plus 5. On the bottom is x minus 3. Oh, I can cancel out x minus 3. Nice. That means it's x plus 5. So that means I can say limit x goes to 3, x plus 5. Now I can plug in 3. That's just 8. All right, so that's an answer. So for this question, I want you to notice that I have a polynomial of a polynomial. I plugged it in. It happened to be 0 over 0, so I'm like, I don't know what to do. I have to do some extra steps. And then like a little trick is I'm going to try to factor. So x squared plus 2x minus 15, I factored into this. Oh, then I have nice cancellation. And then I have this, x plus 5. Now I can take the limit as x goes to 3, x plus 5. Now I can just plug it in, get the 8 answer, right? So this is going to be one of the kind of little trick that I want you to use when you have 0 over 0 case. All right, let's look at part D. Here, find the limit as x approaches to 1, radical x plus 3 minus 2 over x minus 1. So my first instinct was, again, plug in, maybe. X is equal to 1. Let's see what happens. So radical 1 plus 3 minus 2 over 1 minus 1. Radical 4 minus 2 is 0 over 0. Okay, another 0 over 0. Unfortunately, this is not a polynomial. It's like radical something. So how do I simplify this? Again, there's a little trick. So it's called multiplying conjugate. Multiply conjugate. Conjugate in math means I have radical something minus something. Conjugate would be radical something plus something. So exactly the same, except radical, instead of radical minus 2, it would be radical plus 2. So how does that work? Here, let me write it out. Radical x plus 3 minus 2 over x minus 1. So what I'll do is I'll multiply conjugate on the top. Radical x plus 3 plus 2. And then that means I have to multiply exact same thing on the bottom. So yeah, when we deal with the fraction or rational expression, if I did something to the top, or if I multiply something to the top, I have to multiply exact same thing to the bottom. So I multiply the conjugate, that means I have to multiply the conjugate on the bottom. Here, this one has a format of, oh, there's a lot of stuff going on. A plus b, a minus b, right? It's like exact same thing, with the only difference is the sign. So if I FOIL it out, you get a squared plus ab minus ab and then minus b squared. So those ab's are canceling out, so I get this, right? So you probably learned it somewhere in your algebra class at some point. So coming back here, this is my a, this is my b. So a minus b times a plus b. So it'd be just a squared minus b squared. That means in our example, it'll be the first radical squared minus 2 squared. And on the bottom was just the same, right? Nothing cancels out on the bottom or anything. So on the top, we get, let's draw an extra line here. Radical square will just get you x plus 3 without the radical. So it'd be x plus 3 minus 2 squared is 4. X minus 1 on the bottom times x radical x plus 3 plus 2. Here you notice the top part just becomes x minus 1. So they'll just cancel out with x minus 1 on the bottom. So yeah, nice. So it'll be 1 over radical x plus 3 plus 2. So wow. So what happened here? Well, the reason I did all this is because I wanted to simplify, right? Because we had the 0 over 0 case. So now I have to kind of go back. Okay, what was the actual question? I was looking at the limit as x approaches to 1. I had this expression, I simplified it and became that expression. So now maybe I can take a limit now. So the limit x goes to 1 over radical x plus 3 plus 2. Can I plug in now? I think it's possible. Plug in 1 here, radical 1 plus 3, so radical 4, that's just 2. So on the bottom will be just 2 plus 2. So my answer will be 1 over 4. Okay, so we learned kind of two tricks. One is when you have 0 over 0 with polynomial, maybe you can factor it and you can have nice cancellation, then you can plug it in to get the answer. One with the radical, maybe we can multiply the conjugate, have nice cancellation, and then you plug in and then get the answer. All right, let's look at the next part here. It says piecewise limit. Piecewise, sometimes it's piecewise definition of a function. I have a function, then you can kind of see like two functions combined. It's like, why is it there? Why is it there are two functions? Sometimes you want to combine like two functions and split it and then make it into one function. So like here, x is a function, x squared minus 1 is a function. So x will be just a straight line. So they're saying, what they're saying is, when x is less than 1, I get a straight line. So it's like this. And then when x is bigger than 1 or equal to 1, I get a parabola, x squared minus 1. So that's part. So even though it's like two different functions, it's basically one function defined piecewise, right? So which is fine. All right, so let's see. Let's look at the question here. What does it ask? Part A, limit of f of x as x approaches 1 from plus. You see that little plus sign? That means it's the right limit. That means I'm approaching 1, but from the right-hand side. So I'm looking at this portion of the graph. That means for part A, I'm going to ignore the left part. I just look at the right-hand side. So that means my graph is approaching to 0, because again, limit value is the y value. So this one has a y value 0. So I forget the left-hand side of the graph. I only look at the right-hand side, and it approaches to 1, then it's right here. So that would be 0. Another way to think about it algebraically is, this is when x is bigger than 1. So basically, I'm looking at this portion, right? So I'm using this function, plug in 1. 1 squared minus 1 is 0. So that's my answer. For part B, x is approaching 1 from the left. So I'm looking at this graph. Obviously, this graph goes to 1 as a height. So my limit is going to be 1. Again, algebraically, how do I find it? I'm approaching from the left. So that means when x is less than 1. So I'm looking at this portion of the graph. So I'm plugging in 1 to this equation, or this expression. Then you get 1 as an answer. So this will be 1, right? So I can still plug in the numbers. When do I plug in? Like 1, do I plug in 1 here or there? All depends on, is it approaching from the right or is it approaching from the left? All right. We have one last theorem here. It's called the squeeze theorem. Okay, the previous theorem says if one function is bigger than or equal to the other function, then basically the limit of what the small function is less than or equal to the limit of the big function. And squeeze theorem, it basically utilizes a fact. So we have three functions, f, g, and an h, where f is the smallest function, g is the middle function, h is the highest function, right? What they're saying is limit of the f of x, which is the smallest function. So this is the small function. And then limit of h of x, which is the big function. So they're saying the limit of the small function exists, limit of the big function exists, and they're equal to L. So the middle function has to have a limit equal to L as well, right? So middle function has to be always between bigger and small. And then if the big limit and the small limit are the same thing, then the middle function has to have the same limit as well. Okay? And it's helpful when we try to find the limit of a bounded function. Bounded function means functions always stay between like two fixed numbers. It's called bounded. What are some examples of bounded function? What we know so far, I think you should know, is sine function, sine of x. Sine is bounded by 1 and -1. And then same for cosine. Cosine x is always bigger than -1, but always less than or equal to 1. So sine and cosine are two like well-known functions that are bounded between -1 and 1. So let's look at example 5. Show the limit as x approaches 0 of this crazy function sine of pi over x times x cubed plus x squared is equal to 0. Okay, this is very complicated. I don't know what to do. My first instinct was to plug in 0, which is okay for the radical part, because radical 0 cubed plus 0 squared will be radical 0, which is fine. But here, sine of pi over 0, well, pi over 0 is infinity, either positive or negative, so it doesn't exist. So sine of doesn't exist, I don't know what that is, right? So 0 times a number will be 0, but 0 times something that doesn't exist, I don't know what it is, right? So as of now, I don't know if it's 0 or not. So what we're going to do is we're going to use the squeeze theorem. So I'm going to use the fact that sine is between -1 and 1. So this is how I'm going to start. So in order to use the squeeze theorem, I have to kind of come up with the big function and the small function. and I'm going to make the given function, the one I want to prove, to be the middle function. So here, this is how I'm going to start. Sine of pi over x is between 1 and -1. That we know, right? Sine is bounded by -1 and 1. So, but the given function is not sine of pi over x. It's sine of pi over x times this. So what I'll do is I'll multiply that on both sides, or all three sides. X cubed plus x squared times x cubed plus x squared times x cubed plus x squared. So I'm multiplying this to all the side of the inequality. And I also want to make sure that these numbers are positive, so I don't flip the inequality. We're guaranteed that these numbers are non-negative, actually, because it's radical, right? So non-negative, non-negative, non-negative. That's why I don't have to flip the inequality sign. So if that's the case, then I get x cubed plus x squared minus is less than or equal to sine pi over x radical x cubed plus x squared less than x cubed minus plus x squared. So this is going to be, the first one is going to be my f of x. Second one is going to be my g of x. Third one is going to be my h of x. Right? So this function is always smaller than this function, which is always smaller than that function. So g is the middle function that we have. Here I can show that f and h, they have 0 as a limit. So if I look at limit x goes to 0 of negative radical x cubed plus x squared, here is 0 because 0 cubed plus 0 square is 0, radical 0 is 0, negative 0 is 0, right? I can kind of say the same thing about the h of x. Limit of x cubed plus x squared is equal to 0, right? So f of x, this is h of x. So I just show that the limit of f of x goes to 0, limit of h of x goes to 0. So here, by the squeeze theorem, limit of g of x is also 0. Limit of sine pi over x radical x cubed plus x squared is also equal to 0. So when I have to quote, like use a theorem to show something, I have to actually state what theorem I'm using, and I have to kind of rewrite like the condition of the theorem. Theorem says f of x is less than g of x is less than h of x. So I have to kind of show that. That's true for this particular one. So I have to kind of I have to write this out, and then I have to say I'm using a squeeze theorem. I'm going to highlight that part. Right? So on the exam and stuff, you kind of want to say this. If you're using a squeeze theorem, you have to say you're using the squeeze theorem, and you have to write down the conditions of the squeeze theorem. All right, that's it for this section.